Hello everyone, welcome to this very important lecture in the Neural Network from Scratch series. This will be the last lecture in the backpropagation part, and in this lecture, we will be assembling all the building blocks of backpropagation which we have worked so hard for in the previous lectures. So, this is similar to Avengers Assemble. So, I have just put this photo over here. As you will see, each of the building blocks which we have developed are very powerful, and each of them will perform a very specific function when we do the backpropagation. If you have not seen the previous 4 to 5 lectures and have directly come to this lecture, it's totally fine. If you have seen previous lectures, then it's amazing because then you will be able to follow much better. Nonetheless, I'll try to make this lecture as if it's completely self sufficient. And this will be a detailed lecture on backpropagation in which we'll be also going into Python code. So, first, let me explain the problem which we are trying to solve. Here is the neural network architecture which we are considering. So, the neural network actually has two inputs x1 and x2. The first layer has three neurons, the second layer has three neurons, which is also the output layer, and then we have the loss function towards the end. The activation function attached to the first layer is ReLU. The output of the first layer activation goes into the second layer. The activation in the second layer is the Softmax, and then based on the output from each of these three neurons, the loss function is calculated. Let me show you the data set which we have and the problem which we are considering. So the data set which we have looks like this. Every point has two attributes x1 and x2, and every point belongs to either one of these three classes. Either it belongs to the red class, or it belongs to the green class, or it belongs to the blue class. The goal for us is to design a neural network and optimize the weights and biases of the neural network so that given any new data point such as this one, we will correctly predict which class it belongs to, whether it belongs to the R, the G, or the B, the red, green, or blue class. Since this is a classification problem, that's the reason why we have the softmax activation function attached to the output layer. And that's also the reason why the loss which we'll be using will be the categorical cross entropy loss. So this is the neural network architecture, and this is the problem which we are going to solve. Now, in order to optimize the weights and the biases, we need the backward pass, or we need the gradient or the partial derivative of loss with respect to many things in these layers. So let me actually expand this neural network architecture further to first tell you which all gradients will we require. So here's the two inputs, and the first three neurons in the first layer, each neuron has two weights associated with it. So in the first layer, there will be a weight matrix which is W1, and there will be a bias matrix which is B1. Okay, then there is the ReLU activation. The output of the ReLU goes to the second layer, and similar to the first layer, the weights in the second layer will be W2. The matrix will be W2, and the bias matrix will be B2. So every neuron in the second layer will have three weights. So there will be nine weights and three biases in the second layer. And then finally, each of the output of these neurons goes through the softmax activation function. Now, in order to update the weights and the biases of this layer and this layer, we need we need the partial derivative of the loss with respect to W1, partial derivative of the loss with respect to B1, partial derivative of the loss with respect to W2, and partial derivative of the loss with respect to B2. That's our final goal. But to find these partial derivatives, we cannot directly go from the partial derivative of loss to W1 since those are far apart. We need to make a number of jumps, and that's where backward propagation comes into the picture. So let's say if we want to find the partial derivative of loss with respect to W1, let's see the number of jumps which we'll need to make. First, we will need to find the partial derivative of loss with respect to the input to the softmax. That's the first jump which we'll need to make. Let me actually mark these jumps with a different color so that it's easier for you to follow. The second jump which we'll need to make is the partial derivatives of the this layer's outputs, which are z1, z2 and z3, with respect to the weights and biases of this layer. So that's the second jump. So when we have reached up till this point, we have obtained the partial derivatives of the loss with respect to the outputs of the ReLU function. Then we'll have to make the third jump, which is the partial derivative of the loss with of the output of the ReLU with respect to the input of the ReLU. Only after we have made these jumps, we have come to the last stage where we have to find the partial derivative of the output of these neurons, which was the input to the ReLU, with respect to the weights and biases of the first layer. So that's how we are going to get the weights and the partial derivative of the loss with respect to the weights and biases of the very first layer. To get the partial derivative of the loss with respect to the weights and biases of the second layer, we'll just need to do two jumps. But to get the partial derivative with respect to weights and biases of the first layer, we'll need to do four jumps: one, two, three, and then the four. So whenever we define classes in Python, we'll define the forward method as well as the backward method. So the first class which we'll define is the class for a layer. So we'll be creating the first layer which has two weights for each neuron and one bias for each neuron, and we'll be creating the second we'll be creating a class for the second layer. So we'll attach a forward method to this layer class, which will actually take the outputs of, which will find the outputs of the neurons in that layer uh, based on the number of neurons and the number of weights. But for each layer class which we'll create, we'll also create a backward method. What this will do is that based on the gradients which have been received to that layer up till that point. So for example, if you are considering the first layer, the this layer has received the gradients of the loss up till this point, which I'm marking in red right now, which are the inputs to the ReLU. This layer has received those gradients, so that will be the input to the backward method, and the output of the backward method has to be the partial derivative of the loss with respect to the weights and biases of that layer. So we'll add a backward method in this layer and the second layer, which gives the partial derivative of the loss with respect to weights and biases of that layer. And the backward method will receive as an input the partial derivative of the loss with respect to whatever stage we have reached up till that layer. So for example, when we reach the when we are finding the partial derivative of the weights and biases with respect to the second layer, we have obtained the partial derivative of loss with respect to these outputs up till here. So that will be the input, and then we'll find the partial derivative of the loss with respect to w2 and b2. So we'll need a class to define the layers, the forward and backward method in the layers. Then we will also need a class to define the ReLU. When we define this class, we'll need two methods. We'll attach or we'll define a forward method, which essentially just implements the output of the ReLU activation, which looks like this. It is 0 if the input is negative, and then it is equal to x if the input is positive. But it will also define a backward method, which will essentially find the partial derivative of the ReLU output with respect to ReLU input. And remember, up till this point, we have received the partial derivative of loss up till this point. So we have received the partial derivative of the loss with respect to ReLU output. Now we have to find the partial derivative of the loss with respect to ReLU input. So that's what the backward method will do. For the softmax and the loss, we'll implement something special which we looked at in the last lecture. We will not look at these two as separate classes, but we'll club them into one class, the softmax loss class, and we'll define the forward method which will take the softmax and the loss. So it will, so given the inputs as z1, z2 and z3, the forward method will calculate the softmax activation functions such as e raised to z1 divided by e raised to z2 plus e raised to z2 plus e raised to z3, etc. And then it will find the cross entropy loss. And the backward method here will actually calculate the partial derivative of the loss with respect to the inputs to the softmax. And it turns out that there is a very simple formula for this, which we have seen in the previous lecture. So we will need the classes to create layers. We'll need a class for the ReLU, and we will need a class for the softmax and the loss. So let's look at how these classes are created and what are the methods in each class. So when we create the class for the layers, we will of course define a forward pass, and we'll define a backward pass. So when we define the forward pass, we will have two methods in the forward pass. The first method will be the init, which will be called automatically when this layer is created. What this init method will do is that it will initialize the weights and the biases randomly, and it will take as an input the number of neurons and the number of inputs. So for example, this first layer will have two inputs and three neurons. The second layer will have three inputs and three neurons. So the init method will take as arguments the number of layers and number of neurons, sorry, the number of inputs and the number of neurons in that layer. And based on that, it will initialize the weights and biases of that layer randomly using Gaussian distribution. So for example, when we call the init function or the init method on the first layer, it will initialize w1 and b1 randomly. When we create an instance of the second layer, it will initialize w2 and b2 randomly. So that's the init method. The second method, which is in the layers class, is the forward method. What this method will do is that it will take a dot product between the input to that layer and the weights, and then add the bias. So basically it will give the output of neurons. So essentially what the forward method will do for the first layer is that we have three neurons, right? It will give the output of this neuron. So it will give the output of this neuron, and this neuron. And remember, what the neurons are doing is simply a dot product of the input to that layer and the weights of that layer, and then adding a bias term. So that's what the forward method is doing. Then we will have one more method, as we said, and that's the backward method. What this method will do is that it will take as an input, or it will take as an argument, is dldz. This is very important. As I told you before, this dldz is the gradient of loss up till that point. So if we are looking for the first layer, then the input will be partial derivative of loss with respect to the outputs of that layer, which will be the dldz. And we have obtained this since we are doing back propagation. This will be given to us since the first layer will come at the end. So when we accumulate gradients up till that point, we will have found the partial derivative of the loss with respect to the outputs of the first layer, or the outputs of these three neurons. So that's the input here, which this backward method will receive. And then it will find three things. It will find the partial derivative of loss with respect to the weights of that layer. It will find the partial derivative of the loss with respect to bias of the three neurons, and it will also find the partial derivative of the loss with respect to the input of that layer. So if you look at the second layer, the backward method will find the partial derivative of the loss with respect to w2 and b2, which is definitely needed because we need to update the weights w2 and b2 using gradient descent. But you might be asking, why are we finding the partial derivative of loss with respect to inputs? Now remember, the reason we are finding is when we move to the ReLU method, the partial derivative of the loss with respect to the inputs of these layers, so let me mark it with different color. The partial derivative of the loss with respect to the input of this layer, which are the points which I'm marking in green right now, will serve as an input to the backward method of ReLU. Because using these partial derivatives, we'll find the partial derivatives of the input to the ReLU. So that's why when we define the backward method for any layer, we of course find the partial derivative of the loss with respect to weights and biases of that layer, but we also find the partial derivative of the loss with respect to the inputs of that layer, because those inputs are the outputs of the preceding layer, and they are needed for the back propagation in the preceding layer, which is the ReLU layer. So, as I said, we find three things over here. We find the partial derivative with respect to the weights, partial derivatives with respect to the bias, and partial derivatives with respect to the input, given dl dz as an argument. Now, we have seen in the previous lectures the mathematical formulations for this, but I'll explain that to you over here. To find the partial derivatives of the loss with respect to weights of a given layer, The mathematical formula is taking the transpose of the inputs of that layer and multiplying it by the gradient accumulated up till that point. To find the partial derivative of the loss with respect to the bias, we just take the dldz, which is the matrix of the gradients accumulated up till that point, and then sum the rows of that matrix. And to find the partial derivatives of the loss with respect to the inputs, we take the dldz matrix and multiply with w transpose. So remember, to find the partial derivatives with respect to the weight, we have an x transpose. To find the partial derivatives with respect to input, we have w transpose. So that's a good way to think about it. Weights have inputs in the maths formula, inputs have weights in the math formula. So this is the layer class which is defined. In the forward pass, it has two methods, init and forward, and in the backward pass, it has one method which is called as backward. Okay. Now the second class which we will define is the ReLU activation class, and it will also have two things. It will have a forward pass and it will have a backward pass. What will happen in the forward pass is just finding the ReLU of the input. So in the forward pass, we'll just take the input to the ReLU and find the maximum of 0 comma x, which is shown in this graph here. In the backward pass, what we'll be doing is that we'll just take the partial derivatives of the ReLU output of the loss, of the partial derivatives of loss with respect to the ReLU output. That will be an argument or the input to this backward method, and that will be called as dldz. So this backward method, similar to the backward method for the layer, will receive the gradients accumulated up till that point as an input. So if I represent the ReLU box like this, so ReLU, this is the output and this is the input. So we have, in the backward method, the partial derivative of the loss with respect to the ReLU output is given, and then we have to find the partial derivative of loss with respect to the ReLU input. And the way to find this is that we set it equal to the dldz, which is the partial derivative of the loss with respect to ReLU output, and wherever the input is 0, we set this to 0. So we have the inputs which are coming to this ReLU because we calculated during the forward pass, and wherever the input is, so this should be actually less than 0. So wherever the input is less than 0, we set the that particular elements in the matrix to 0. And that's just how the derivative of the ReLU happens. So if x is positive, the derivative is 1. If x is negative, the derivative is 0. I'm going a bit fast here, but I have a special lecture directly dedicated to ReLU activation and how to do the backward pass. So please refer to that lecture in this series. But for the sake of completeness, the way to calculate it is just first set the partial derivative or the answer to dldz, and wherever the input is less than 0, so find the input which is the z matrix, which is the inputs coming into the ReLU. Wherever that is less than 0, you set those particular entries in the dldz matrix to 0. And remember, dldz is the partial derivative of the loss with respect to the ReLU output. So that is the backward pass. And then the third class which we'll be looking at is the softmax plus loss. So this is what I explained over here. The trick which we have is that we'll not define separate classes for softmax and loss. We'll combine both of them into one class, the softmax plus loss class, and we'll define a forward method and the backward method. In the forward pass, so in the forward method, we'll take the softmax of the output and then we'll apply the cross entropy loss. Remember, the cross entropy loss is just a summation of negative of y true multiplied by log of y of the prediction, which is the summation of true values multiplied by log of the predicted values, and we take a negative sign. And in the backward pass, essentially we have to find the partial derivative of the loss with respect to the softmax inputs, and that actually turns out to be a very simple formula, which is just the predicted values. So these values which are predicted by the softmax, and we subtract the ground truth. So in the previous lecture, we actually saw the implementation of this in Python and also on the whiteboard. But if you are seeing this lecture from scratch, or if you have not seen previous lectures, just remember that In the backward method of the cross entropy plus loss class, it's actually very simple to um, calculate the backward pass. So it's very simple to calculate the partial derivative of the loss with respect to the softmax inputs. All we have to do is just subtract the ground truth values from the predicted values. So let me just minimize the screen a bit and show you what all we have seen up till now. So we have seen that there are essentially three building blocks. The first is layers, the second is ReLU activation, and the third is softmax plus loss. And we have a in each of these building blocks we have a forward pass and a backward pass, and there are different methods in the forward and the backward pass. So if you look at the screen right now, this is all what the back propagation building blocks are. Each of these building blocks carry a very specific purpose, and each of these building blocks are needed to do the back propagation on the entire neural network. In the next module, we are going to look at how to essentially put all of these building blocks together in the code, and how to run one forward pass and run one backward pass in Python. So I hope you really enjoyed this lecture, because the main purpose of this lecture was to not hide anything from you, but to show you how all the things come together. So we had a lot of lectures on backpropagation, and this was what it was building up to. Now we have everything on one page, and I'll show you in Python code how simple it is to assemble all of these things together once we have written the forward pass and backward pass and the different methods on the whiteboard. So stay tuned for the next module, in which we will be going into Python and coding this out in Python. Thank you so much, and I look forward to seeing you in the next module.